before we tackle these synthesis problems from chapter 21, I thought it would be useful to summarize some things to keep in mind for these synthesis questions. And although you can't memorize your way through organic chemistry, sometimes it's helpful to have these little shortcuts. So just as a review, when you do an aldol condensation, the product is a beta hydroxycarbonyl. So that means that the hydroxy group is on the carbon next to the carbonyl. And if you do the condensation, then you get an alpha beta unsaturated carbonyl. When you do a Claisen condensation, the product is a beta ketoester, or you can think of it as a 1,3-dicarbonyl. If you do a Michael or a Stork enamine synthesis, which are both conjugate additions to alpha beta unsaturated carbonyls, the product of that is going to be a 1,5-dicarbonyl. And here you're going to use the Stork enamine synthesis if the enolate would be too strongly basic to do a conjugate addition. Because again, what you're doing here is you're doing an addition of the nucleophile, which is the enolate, on that beta carbon. And then going back earlier into the chapter, you can alkylate alpha to a carbonyl, just a regular carbonyl, using an enolate and an alkyl halide. That's an SN2 reaction. In this reaction, your alkylating group is acting as the electrophile, the enolate is the nucleophile. You can alkylate beta to a carbonyl via the addition of a cuprate reagent to one of these alpha beta unsaturated carbonyls. So in this scenario, the alpha beta unsaturated carbonyl is acting as the electrophile, and the alkylating entity is acting as the nucleophile. So just some stuff to keep in mind. And so now we'll go back up to the top and start working through the problems. Right. So in this first one, we have cyclohexanone, an ordinary ketone, and we need to make this product out of it. So some things you're going to notice. First of all, it's pretty clear which part of the product came from the starting material. So there's our new carbon-carbon bond. Also, we have a 1, 2, 3, 4, 5 dicarbonyl compound, and so we need some sort of a conjugate addition. And here we're going to use an enamine because the enolate piece is going to come from here, and the alpha beta unsaturated carbonyl compound, which is this piece working backwards, is going to come from this compound. So again, we have to use the Stork enamine synthesis. And so the first thing we do is we take our starting material, we make the enamine, and then we add our pre-selected Michael acceptor and do a hydrolysis. And the hydrolysis accomplishes three things. One is it hydrolyzes the intermediate aminium that you get after this addition to the carbonyl. It protonates the oxygen, the O- oxygen, to make an enol, and then it tautomerizes that enol to the keto form. You could, if you were writing this out as a synthesis, do this as a 1, 2, 3 thing because you don't isolate necessarily this intermediate enamine. So in this next problem, I'll slightly hide the answer here. In this next problem, we have a 1,3-dicarbonyl as our target molecule, and therefore you should think Claisen. Clearly it's going to be a mixed Claisen because these two pieces don't look anything like each other. In order to do a Claisen, we need an ester, and so we can take this compound and make it into an ester. And again, our new carbon-carbon bond from our Claisen is going to be between the carbon that got attacked in the nucleophilic acyl substitution and is therefore still a carbonyl, not an ester, and then this other piece. So there are our two pieces, with this being the carbonyl piece and this being the enolate piece. And here's a case where we're going to have to do a Directed Claisen, well, we always pretty much do a directed Claisen, but in any event, both of these have alpha hydrogens. So we're going to take our initial carboxylic acid and turn it into the ester. Right? And then, since when you do these directed Claisen or aldols, you have to add the compound whose carbonyl you want to react to the enolate. We kind of have to do a second phase here. So we take the ester that we want to make the enolate of, we use LDA to make the enolate, and then we add this ester, which I didn't feel like rewriting, slowly, and then finish it up by adding water. All right, in number 3, here we have another 1, 2, 3, 4, 5 dicarbonyl compound. So again, we've got our conjugate addition. Since the reactant has a 1,3 dicarbonyl, we can make an enolate of this, and that enolate will be weakly basic enough to do a conjugate as opposed to a direct addition. So we don't have to do the whole enamine thing. And so kind of working backwards, looking at this in view of this, if we take this compound, we hydrolyze it and it decarboxylates, that will give us this compound. And this compound arises from the starting materials, enolate, and this alpha beta unsaturated compound. So working our way forwards, we start with our starting material, and you just need sodium methoxide to remove that proton. That makes the enolate here. We then add our pre-selected Michael acceptor, and we do a hydrolysis with H3O+. And I actually did this in 2 steps. Really what you would do if you were doing this is you would add H3O+ and heat, and it would do that whole thing. I just wanted to show the intermediate. So if you just hydrolyze that and no heat, you should get that compound. And then if you add H3O and heat, you'll hydrolyze that's really not the right word, but you'll convert the esters to the carboxylic acids, and then it will decarboxylate. So again, this step will convert the ester to the carboxylic acid and then heat. And I honestly don't know how much control you have over this situation. So if you just add acid, you might get this, you might get the dicarboxylic acid, or you might even get some of this. So as I said, in real life, you would do these 2 things together. So in this problem, we have sort of a masked carbonyl situation. So remember, if you have an alcohol, you could make a carbonyl. If you have a carbonyl, you can make an alcohol. So this is immediately derived from the reduction of that. And again, we have kind of obvious pieces based on our starting material. So this is going to be the enolate or nucleophile piece. This is going to be the alpha beta unsaturated. And we know that because, again, we have a 1, 2, 3, 4, 5 dicarbonyl. And since our starting compound that's going to be the nucleophile only has 1 carbonyl, again, we're stuck with a Stork enamine because the enolate only has 1 carbon, 1 carbonyl. So working forward, we take our, show that a little bit better. We take our starting material, we make the enamine, we add the Michael acceptor, and then we add again our H3O+, which does the same 3 things it did in, was the first one or the second one where we used an enamine. And then with excess sodium borohydride and ethanol or methanol as the solvent, we can reduce the ketone in the aldehyde to primary alcohol and secondary alcohol. So finally, we have this one, which has a little bit of a twist to it. So we're taking this alcohol and we're making this. So if you compare this piece to this piece, it's pretty apparent that this probably needs to get turned into a carbonyl. Besides, we're dealing with a chapter on carbonyl compounds. Sometimes students get put off a little bit by this, which looks a little bit strange. But if you think about it, what we have here are two oxygenated carbons that are 1, 2, 3 apart. And so from an aldol condensation, without any protonation, we could get something like this, or if you prefer, you could think about this is coming from the aldol condensation, that beta hydroxycarbonyl. And so that could come from the aldol of, the directed aldol of these two compounds. That one's sort of falling off the thing there. And then we can just alkylate the result. So, moving forward, we're going to take our alcohol and oxidize it with most anything to make this ketone. And then we need to do a mixed aldol here. It doesn't matter whether we do a directed aldol or not, because this thing has, this benzaldehyde has no alpha hydrogens. So, and this is a ketone carbonyl. So we really don't have to worry about getting the wrong product to any great extent. There would technically be nothing wrong with doing a directed aldol here, but it's a lot of work. So why do it if you don't have to do it? So if the base is strong enough, we're going to get this as an intermediate, and then we could just directly add ethyl bromide to it. If you preferred, you could think about this as making this compound, and then you could remove that OH and then alkylate it with the ethyl bromide. Most of these problems, by the way, are either problems from Klein or they're adapted from problems.